Yeah, that's even job.
Yeah. I know.
You're not allowed. Like they made it a school wide thing where it's like you're not allowed to do that for accessibility reasons. But
I know. It used to be so much technology that was it's so outdated. Science, where it's just like bullet point do this, but yeah, nonsense. They literally don't make sense. Some of them. I almost jumped over the desk.
that was like my experience with David. Yeah.
That students are objective, or out. Students are outputs, and that all these students do well. So fine. Like students end up in healthy. That's not correct. Like what the fuck are you talking about? He doesn't do anything. He has a volunteer research that does everything. I told him, send him a 140 line markdown file of all the changes I would make to his site. Not even that I think it's switch to Canvas. Like just all this technology that's all makes out.
Yeah. Okay, good morning, everyone. Can you all confirm if you can hear me clearly? Okay, I want to welcome you to another multivariate statistic class. Before I get started, I want to remind you, next week is midterm. Of course, I've already posted midterm one, practice questions with solutions. And of course, next week, I think Monday, we're gonna go over those questions, and I'm also gonna tell you what to bring to the exam or among other information. So that will be by next week, Monday. Okay, so the topic we are starting today, it's not gonna feature a midterm one. Of course, because mid time two is not cumulative. So whatever we start today, we actually be in midterm two. Does that make sense? So this is like we are counting down, starting this topic, this is going to take us en route to midterm two. So I want to welcome you to another interesting multivariate statistical topic that we call inferences about multivariate means. Okay, inferences about multivariate means. Okay, so in the outline, I'm actually going to start with what we call single mean vector. Okay, then from there we're going to talk about multiple mean vectors. Of course, before now, in a lower level statistics, you've heard about one sample t-test, two sample t-tests. You've heard about analysis of variance. All of that actually focus on one measurement at a time. I'm going to say that again. Your one sample t-test, the two sample t-test, and and the analysis of variance tests you've done in the past are actually focused on univariate. But what we want to do now is how can we extend one sample t-test, the two sample t-test, the analysis of variance tests, from univariate to multivariate situation where we're no longer focusing on a single response, but we are focusing on what I'm actually going to call dimensional response. Okay, so we're going to talk about how we conduct hypothesis testing involving multivariate means. We're also going to talk about how we construct confidence interval as well. Let me remind you, statistical inference is about constructing confidence interval and testing hypothesis. Okay, uh, I first want to start with inferences about single mean vector. And when I say inferences, of course, I mean how do we test hypothesis about it, and how do we construct confidence interval? Okay, you know, uh, if I want to, if I, for instance, if I want to focus on one sample t-test for multivariate, I need to first understand, or have a recap on one sample t-test for univariate. Of course, before now, you've done one sample t-test for univariate. So we first want to have a recap on that, so that from there we'll now generalize to a multivariate situation. Now, of course, we have assumption here where you have your observations and you're focusing on one measurement. Okay, the x1 up to xn is just the number of observations within, I'm only focusing on one variable. And of course, assumption is that we're going to have that follow a normal distribution. Of course, that is one of the requirements of a one sample t-test. Uh, your data set have to follow normal distribution because the one sample t-test is a parametric. I'm actually going to write that. It's a parametric test. Okay, so parametric tests actually rely on the assumptions of normality. And that's why we actually expect the distribution of our data set to follow normal distribution. And you know what we normally want to do, we want to test hypothesis because, there can be a claim. And whenever there's a claim, investigation follow a claim. What if a particular company claim that okay, the average maybe the average household income in United States is a particular value, and the alternative is that it is not. So whenever there's a claim, investigation follow a claim. Okay, and part of investigation procedure is you conducting hypothesis. Okay, so if you take a look at what I have here now, well, this is the non-hypothesis and this is the alternative. Okay, and this actually focus on mean. Okay, and mean, we're focusing on one measurement at a time, like call univariate. Now, whenever we have a test, you know, of course, in one of the procedure in a step in hypothesis testing is formulation of your hypothesis, which we have already done here. Okay. Uh, the alternative here is can actually take or three type. It could be a two tail like that, where we say it is not equal to, it could be less than, it could be greater than. Of course, you've come across that in the lower level statistics. And the moment we formulated our hypothesis, the next is the test statistic. Okay. The test statistic is actually it's a t-test, so that's going to be t equal to the sample mean minus the hypothesized value divided by the standard deviation divided by the square root of the sample size. And of course, the X bar here is actually sum of when you sum your data and you divide by n. And of course, um, this is the sample variance. You have to use the variance, the one that is divided by n minus 1, because of the fact that we want to maintain what we call the unbiasedness properly. Okay, so we're going to use that. Okay, now, now, and uh, we normally have absorption situation. Here, I'm actually using t-test. I'm using t. I'm actually going to use t in a situation, where sigma square, the population variance is unknown. If the population variance is known, I'm not going to use a t-test. I'm going to use a z-test. We have a t-test, we have a z-test. Okay, so when the population variance is known, I'm going to use a z-test. But when the population variance is unknown, I'm actually going to use a t-test. So what are we doing right now? I'm actually reviewing, I'm having a recap on, one sample t-test for univariate. And of course, we believe that the distribution of that test, the test statistics actually will follow student T distribution. Like I said, we use the test when the population variance is unknown, but when the population variance is known, we use a Z test, and of course, we're going to be checking from Z table. We have a T table. We also have a Z table. Okay. And of course, we're going to take a decision on whether to reject the non-hypothesis or not, depending on where, if your the p-value associated with the test, if it is less than a given level of significance, of course, you're going to reject the echelons. But if it is greater than that, you're going to fail to reject echelons. Okay. But you know what we want to do right now? We actually we want to work with more than one variable, okay? Because in the conventional t-test, we only focus on one variable at a time, okay? What if in a situation where we want to simultaneously focus on more than one variable at a time? So, which means the T that we have here, the T test that we actually have in here, okay, can we have a way to rewrite that? If you take a look at this, if I square both sides, if I square this, I'm also going to square that, okay? You know, uh, the provided I treated them the same way, uh, situation where you're not going to alter mathematical, standing is when you treat the both side of the equation the same way. So if I want to extend this to multivariate version, okay, if I want to extend the conventional t-test for univariate to or multivariate version, okay, I'm actually going to square both side. When I square both side, okay, I just wanted to see what I'm going to have when I square both side. Okay, when I square both side, I'm actually going to have this. Take a look at this. Okay, I'm actually having this. Don't forget, initially, I got it is t equal x bar, okay, minus mu, okay, divided by standard deviation divided by square root of n. Okay, now when I square this and I decide to put a square on that, okay, so x bar minus mu will appear twice. That's why you're seeing it here. It's also saying it here. Okay. And the S at the bottom, we have it squared, right? And by the time it goes up, I don't want denominator anymore. Okay. It's actually going to become this guy. And this guy here, square root of n, this is more or less like I have 1 divided by 1 divided by square root of n, which is also going to be square root of n. When I square root of n, that is going to be n. So what I've done here is trying to square the test statistic for one sample t-test, for the one for univariate, I squared that, and this is what I got. Now, if I get this guy now, I actually want to make sure I convert this. I want it to be in a matrix form. Of course, to be in a matrix form, this guy is just going to be talking about the inverse. Okay, inverse of a matrix. And what I'm going to do, if you take a look at this guy and this guy, I'm actually going to put transpose on 1. Okay, and when I did that, I just wanted to take a look at something here. What is going to happen in the end? Okay, now based on what I have here, based on what I have here, okay, based on what I have here, I can convert that to look to actually be in line to align with the multivariate the multivariate sections. Now take a look at this one now. If I now want to go into multivariate now, okay, I'm actually gonna say I do not have one variable, but I got so many variables. Now in that situation, okay, all the variables will now follow multivariate normal. You can see the connection between the topic that we are starting now and what we finished yesterday on Monday. What we finished on Monday, we talk about multivariate normal distribution. Okay, if I want to conduct one sample t-test for multivariate, we expect the variables under investigation to follow multivariate normal distribution. Of course, for one sample t-test for univariate, okay, the variable under investigation follow normal distribution, the univariate normal. So this is multivariate normal, where the mean here is actually going to be vector mean, and this guy here would be a covariance matrix, which is what I'm actually defining now. Don't forget, we're taking this from what we did on Monday. Okay, what we did on Monday is very, very crucial when you are talking about if you want to conduct statistical inference for multivariate means. So we're going to have xi, x1 up to xp. Now, if I want to, maybe I'm talking about clinical variables. Okay, maybe I want to conduct a one sample t-test for multivariate in a clinical setting. Let's have an example. Okay, maybe my x1, maybe my x1, may actually represent so SDP or SBP, systolic blood pressure, and maybe S2, okay, maybe it's diastolic blood pressure, maybe X3 is cholesterol, maybe cholesterol, just wanted to make a sense. Now, if you take a look at what I have here, for the case of a univariate, one sample t-test, we're only going to focus on only one variable at a time, one of these. But now, we want to focus on all these three. It means a particular, maybe the hospital here, the clinic, actually want to investigate whether patients enroll in a maybe a new style program have achieved what I'm actually going to call a standard cardiovascular benchmark. Maybe the association of American Heart Association sets what I call a benchmark for SDP, for DBP, or maybe they put a benchmark at 120, 120, 80, and 100. You know what? If this is a benchmark, this guy here is actually the mu zero, which is an hypothesized mean vector. This is an hypothesized mean vector. So the clinic may want to test whether the patient enroll into a new style program have achieved this benchmark. If they're going to do that, they're actually going to conduct a one sample t-test for multivariate. So, which means our X here now that I talk about, okay, these three, okay, these three will be actually be collected from patient, all the patient. Each patient will produce three response vector like this. Does that make sense? Okay, so that's what I mean. Now, the question now is, why do we need to conduct a multivariate? Why do we need to do one sample t-test for multivariate? Why can't we actually achieve this one at a time? Why can't we focus on SBP? Why can't we use a conventional t-test? Okay, for univariate, focusing on SDP separately, focusing on DPP separately, focusing on cholesterol level separately. Okay, why are we not able to do that? Why do we need to simultaneously test these? Okay, the reason why we need to simultaneously test this is because the variables may be correlating. When variables, if you use the conventional one sample t-test for univariate for this, you are ignoring correlation among them. When you ignore correlation, you undermine the variance. When you undermine the variance, your test, your results cannot be relied upon. So the multivariate analysis, the multivariate technique will enable us to capture the relationship that exists among the variables. And that's why we're using that. But you know what? Because of the fact that we are equipped with matrix knowledge, matrix algebra knowledge, we're never going to have issue. We're actually going to use the idea of a matrix algebra knowledge here. Okay, now I need you to pay attention. The other time, where we're talking about univariate, one sample t-test, I said when the population variance is known in advance, there's a difference between population variance and sample variance. The sample variance is the one you get from the data. The population variance, okay, at times may exist and it may not exist. When the population variance exists, you use a z-test. When the population variance does not exist, you're going to use a t-test. Also, under a multivariate, we're also going to consider situation. In a multivariate, we don't talk about variance. We don't talk about variable, we talk about a covariance. That guy is a population covariance. So Suppose a population covariance is unknown. Okay. Now we want to test this hypothesis now. Take a look at this hypothesis. This mu zero here is a vector. It's not a scalar. Does that make sense? Okay. Now, if you want to test that, we're actually going to use or the test statistic is Ottolini squared. Okay. And you know what? You remember the other time from the classical one sample t test for univariate, I said we should square, right? You know, that actually give us a t squared the other time equal n, and the other time we only have x bar minus mu, right? Then we have sigma squared. We got sigma squared raised to power -1, then we have x bar, okay, minus mu, okay. But if I want to write it in a multivariate way, okay, now this is n, this is also n, then I'm only going to do I'm going to turn my x bar to that, so that that's going to reflect a vector, my mu to mu naught. Then I'm going to put a transpose on one. I'm not going to put a transpose on the other one. But you know what? Take a look at this guy. It's the same as that sample covariance. In a univariate case, we just call it this S squared. In a univariate case, we call that sample variance. In a multivariate case, it's an uppercase S. We call that sample covariance. Does that make sense now? You know, the reason why students at times struggle with statistics is because of the fact that they don't pay attention to notation. So if you pay attention to notation, if you understand what each notation, what each symbol represent, you're actually going to be fine. So because of that, look at what we are having now. We're having what we call, or this is what we call Ottolini squared. Okay, so what you have here is what we call Ottolini t squared. Ottolini t squared is actually a test, statistic that we apply for one sample t test, in a multivariate setting. Now, we now want to define, for instance, moving forward, I need to be able to compute t squared. And after getting t squared, if I know the distribution for t squared, then I will be able to get a p-value associated with t squared. And don't forget, the p-value will enable me to take a decision regarding the hypothesis under investigation. Now, but you know what? I guess how do I actually obtain each of these? Of course, I know that is in the end is the number of observations that I have. Okay, and now am I going to get the X bar? Of course, you're going to get, if you have three means, if you have three variables, you're going to have the mean. You can get the mean of each. The mean of each. If there are three in number, that will form your sample mean vector. Okay, what about the mu naught? The mu naught will be an hypothesized values. I said something the other time about a clinic trying to see whether some patient enroll in a style program have achieved what I call a standard cardiovascular benchmark. And that was set by American Heart Association. They said that for systolic blood pressure, they put the average to be 120, and they put for the systolic blood pressure to be 80, and of course the cholesterol to be 100. Okay, and that's going to be the mu naught. That's an hypothesized value. And of course, before you can get the inverse of a covariance, you need to first get the covariance. Okay, using that. Okay, now after you've done all of that, I need you to pay attention. Okay, now, before now, I walk you through. If you remember what we've done before, I remember when I was when we're discussing on data matrix. From data matrix, we're able to get the covariance matrix. Before getting the covariance matrix, we actually get a centered matrix. So you can also use that approach. Okay. You can also use that approach to be able to get that. Okay. Now, I want you to pay attention now. If I obtain my t squared, please pay attention. If I obtain my t squared, okay, because of the fact that we actually want to take a decision using p-value. Has anybody heard about p-value? Okay. Now, because of that, we need to be able to know the distribution. What is the distribution? When the null hypothesis is true, okay, and we realize that the Ottolini squared actually follow this, okay, it follows F distribution. Look at that, F. We got 2 degree of freedom, P degree of freedom, N minus P degree of freedom, okay. Now, if I want to find the p-value now, okay, take a look at that. I'm actually going to find what is the probability of a t squared greater than that, because you know what happened? The p-value is actually talking about what is the probability of rejecting, for instance, you have of experiencing an extreme value when the non-hypothesis is true. I'm going to say that again. P-value mean, they want to figure out the probability of observing an extreme value when the non-hypothesis is true. Okay, so now your alpha, which is the level of significance, the level of significance is the maximum probability of committing type 1 error. Okay, so when the p-value of a test is less than the level of significance, of course, we're actually going to reject the non-hypothesis. Okay, so the distribution here is actually F distribution. We can check F distribution in from a statistical table. Okay. Now, let me tell you this. We got 2 ways of taking a decision when you conduct a one sample t-test for multivariate. It's either you make use of your p-value or you compare these two. You compare this. Okay, where the t squared is actually going to be what you get for your test statistic value. You're now comparing that with a critical value. This guy here is a critical value. When the t squared, when the test statistic value is greater than the critical value, where will the critical value come from? The critical value will come from the table. Now, when t squared is greater than that, okay, you're actually going to reject the non-hypothesis. So it's either you use that or you use your p-value. But to be able to reject the non-hypothesis, the p-value associated with your test statistic has to be less than a reasonable level of significance. Okay, now, can we have a way to compare the student t squared and the Ottolini t squared? The student t squared is what you use for the conventional one sample t-test for univariate. Is there a way we can actually compare that with the Ottolini t squared, the one for multivariate? And I need you to pay attention. Okay, let's pay attention. Okay, now this is it. The one for univariate, okay, is a lower t squared. Okay, the one for univariate, this guy here, take a look at this. UVN. I'm talking about univariate. It has to be univariate normal. UVN means univariate normal. Okay, univariate normal. And the distribution, okay, when you take a look at this guy here, please pay attention. I'm actually starting from here. Okay, this guy is a univariate normal. This guy here. Okay, now this guy is a scale chi-squared. It's a chi-squared with a degree of freedom. Okay, and of course, this is univariate normal. But in the case of the multivariate one, We don't talk about univariate, but we talk about multivariate. MVN means multivariate normal vector. That's multivariate. And this one, the distribution is not going to be chi-square. It's going to be Wishart. Okay? Wishart is a multivariate version of a chi-square. Chi-square, we use that for univariate. Okay? So take a look at that. So I just wanted to see the difference between the two. Okay. Now, I need you to pay attention now. How do we do this in R? How do we do this in using a statistical software? And I need you to pay attention. We got hard way to do it. We got easy way to do it. But you take a look at this. If I actually, if I want to achieve this now, I'm actually going to go to the formula for the Ottolenghi squared. Okay. Now the Ottolenghi squared. Do you see this formula? That's what I want to code. I actually want to code this guy. Okay. I want to code that guy. Okay. And how do I code that guy? And I need you to pay attention. And after coding this guy, I also need this guy. I need this guy as well. Can you see that? I need that guy as well. Now let's see the way the coding is gonna work. Let's see the way the coding. Now I'm gonna write t dot s, okay, less than minus function x mu equal to 0. Okay, x is going to be a matrix, data matrix x. Okay, now of course the matrix is going to have dimension, right? There's going to be number rows, there's going to be column, I need n and p. Okay, where is the n and p coming from? If you go back to the formula, there's n and p in the formula, right? Look at that, n and p here. Okay, you need n and p in the formula. Okay, and that's why we're writing that. You see, n and p, then the graph n minus p. Look at that. Now I need to code. Now this code here is all the way to the p-value. If you take a look at this, all the way to the p-value. Can you see? Can you see the p-value? All the way to the p-value. Okay. So if you take a look at that code now, this will enable you to test. And you know what? You're going to be wondering, where is the t-square formula? Is it not this guy? Can you see that guy? That is the t-square formula, which is n. Okay, you can see n multiply. Okay, we have transpose x bar minus mu multiply solve s. Solve s means find the inverse of the covariance matrix. That's what it means in R. Solve S means inverse of a matrix. If I want to find the inverse of a matrix A, I'm actually going to say solve A. Okay, so take a look at that. Now I got the code. We are actually included a p-value. The moment you have your data, you automatically you're going to generate a p-value. Okay, now we now want to apply this to real data set. I will advise you to check, to work on this. We have data set embedded in R that we call empty cows. Okay, in this empty cows, please pay attention. We got more than one variable. Can you see the variables in it? MPJ, DISP, HP, WT. So which means here we have a multivariate. Okay, not just one measurement at a time. Okay, now we try to get the mean of each of these variable because in the formula we need the mean of each of these variable. This is the mean. This very mean here, this is sample mean. The sample mean. Does that make sense? The sample mean. And we need to also have an hypothesized value for the mean. And that is actually going to be the one we're going to write in the non-hypothesis. In the non-hypothesis a show, okay, where I'm actually going to say mu equal. Now, you're actually going to be given that. That is what it gave you. Oh my God. This is an hypothesized value. Okay. Maybe they say for NPG, they're hypothesizing 20. For DISP, they're hypothesizing 200. And for HP, they're hypothesizing 150 and 3 for the other one. Now they're trying to say under the non-hypothesis, HO equal to that. Under the alternative, it's actually saying H naught is not true or it's not equal to that. So here, this guy here, what it specify here, that is where you're going to specify your hypothesize or mean vector. Okay. Now, after that, then you write the code. When you write the code now, you're actually going to get a result. Let's take a look at the results. Okay. Now pay attention in the results. In the results, okay, this is the value of the Ottolenghi squared. Imagine I gave you an exam and I say, okay, can you write, what do you get for the, maybe I wanted you to get the t square value, the Ottolenghi square value. Now, if you use R or you use calculator, okay, you should tell me for this data is 10.78587. Okay. Now, the 2 degree of freedom. Okay, the DF1 is actually talking that is n numbers of, sorry, it's talking about P, okay, which is 1, 2, 3, 4 MPG, DISP, and something like that. What is important now here? Let's see what is important. This guy here. That's a P value. Okay, do you see that P value? Now, when you take a look at the P value now, okay, with the P value of 0.07 is greater than 0.05. The standard level of significance is 0.05. When p-value is less than the standard level of significance, you reject H0. But because of the fact that this p-value is greater, we're going to fail to reject H0. Okay, failing to reject H0, it means, what you get is actually aligned with the hypothesized values. It's like your data agree with the hypothesized values. Just like the example I cited the other time about a particular clinic, after enrolling patients into a stylish program, they're trying to see whether the patient have actually achieved what I call a standard cardiovascular benchmark, okay, set by American Heart Association, Heart Association. And of course, if you have a p-value like this, then it means, they've achieved that. And of course, if the p-value is less than a level of significance, of course, you're actually going to say they did not achieve that. Okay. There are different ways we can actually achieve Ottolenghi, this coding now. If you want to go by making use of LM, that we call linear model, you can also use that. Okay. If you take a look at the code that we have, you're going to go by way of analysis of variance way. Okay. Of course, if you're going to go by way of analysis of variance way, of course, we're also going to achieve that. And of course, in the end, you're going to see, if you take a look at what I have here, okay, you can see the p-value for what we did the other time. Let me take a look at this guy here. If you want to go using the analysis of variance way, we still have the same p-value that we got the other time. Okay, whichever way you want to go, there's so many ways, to code. It now depends on you. It depends on the one that you actually want to adopt. Okay, now so that is for that. Now, when you take a look at this one too, okay, if you take a look at this is another way, okay, that we can actually achieve that. The p-value is, but the one that we actually recognize is the first one that I show you. Most people use that. Okay, now we want to go back to, because of the fact that we are operating under the assumptions of multivariate normal distribution. I remember on Monday, I walk you through how do we, because if you need a sample mean vector and you need a sample covariance vector. So, and you know what? How do I know the formula to use? How do I know that I'm actually going to use for mean? How do I know I'm going to use summation x over n? Okay. We got now. I need you to pay attention. I want to say something now, and I need you to see, just be focused. You know, the formula that we use, the formula that we always use, they actually come from somewhere. And the formula will only be appropriate if we are assuming the data is also come from where the formula come from. Let me put it this way. The formula was derived assuming an underlying probability distribution. And what are we assuming here? We did this on Monday. This is, we can get the mean, the maximum, using the method of maximum likelihood, we are able to get the mean and the covariance. Okay. If you take a look at these two, okay, we derive them from assumptions of normality. Because if you take a look at this we use maximum likelihood assuming a multivariate normal. Okay, and that was what we use to find the mean. Okay, and to find the covariance, the estimate of the covariance matrix. Now let me tell you this situation where the data you have at hand do not follow normal distribution. That means using this formula, you're actually going to mislead, because the formula is actually coming from the assumption, was derived from the assumptions of a normal distribution. Then your data set too must also come from a normal distribution. It's not as if our models are failing us. Maybe we're the one that we're not doing the right thing. We want to extract meaningful information from data using a model. Model is like a formula. Okay. Now, the two of them have to agree. Okay. Have to agree in the sense that they have to come from the same probability generating mechanism. That's exactly what I mean. We don't just do what we do. We got a reason for doing what we do. Now, I need us to pay attention now. Okay. Please pay attention. Okay. Now, I want us to look into this. I want to go by way of maximum likelihood approach. And I want you to see something. Because in a multivariate statistics, if I want to conduct this test, we also have a maximum likelihood approach that we can use. Let me tell you this. When I have a multivariate normal and I use the method of least squared, the method of least squared will also give me the same thing as this guy. But if I want to talk about this guy, there's a difference between the formula for the covariance that I'm actually going to get using the least squared and using the method of maximum likelihood. Using the method of maximum likelihood, the difference is going to be divided by n. But using the least squared, it's going to be divided by n minus 1. But we're also okay with this. The one from MLE is actually biased, but is going to be asymptotically unbiased. When the sample size increases, when the sample size is sufficiently large, we expect the MLE covariance to behave like a least square covariance. Okay. If I want to go by way of MLE, please, I need you to pay attention. After optimizing this, we came out with this. You know what I'm going to do? If I come back here, wherever I see mu, I'm actually going to plug in that in this. And wherever I see that, I'm actually going to plug in that. It's like plugging in the optima into the likelihood function. When you do that, when you plug that in, this is what you're going to get. This is what we're going to get. Okay? That's what we're going to get. But you know what? I don't expect you to know how to derive that because this course is called Applied Multivariate Statistics. But if I'm teaching a master or if I'm teaching somebody that is doing maybe a master's or PhD in statistics, then we have to show this from the first principle. But what I just want you to know now is this is what we're going to get after we put in back the optimal value into the likelihood structure. Now, I just wanted to take a look at this guy now. What do you see? This is now based on the covariance because every other thing is just the number, or n is the number of observation, or p is the numbers of the variables, and the most important thing is this guy. Do you see that? That is the most important thing. Okay, now I'm not going to have to, don't forget, we have to hypothesis. Now I want to look into this. When the non-hypothesis is true, okay, under the non-hypothesis, okay, I'm actually going to plug in wherever I see mu, I'm going to put mu naught. Wherever I see covariance, I'm going to put covariance naught. Now, take a look at this. What do you see now? What changed? What changed from here to here? The only thing that changes, I'm assuming when the non-hypothesis is true, okay, the covariance I will be talking about will be the covariance associated with the non-hypothesis. Does that make sense? And how am I going to get a covariance associated with the non-hypothesis? It is this that I got before. Okay, now I just want you to take a look at this. Give me 1 second. This guy here, I only put naught, mu naught. When we got that before, it was this. Can you see that? Can you see it? This is general. Okay, so this is going to become, if I'm talking about H naught, this is going to be, I'm going to say, oh, this one, I'm talking about the estimate of covariance when the non-hypothesis is true. Then here, because the covariance here depends on the mu, I have to put mu 0. I also need to do mu 0. But if I'm talking about the alternative, then it's just going to be mu or mu 1. Okay, that's exactly what I'm doing there. That's what I'm doing here. Can you see that? So that is MLE under that. Okay. Now, if that is what I have, okay, which means, please pay attention. Please pay attention. Now, we want to use another approach where I'm going to start next time. You know what? You know this building, what I'm doing? I'm trying to see, can we use an idea of a likelihood ratio test? Which is another way. Likelihood ratio test would mean, I'm going to compare, I'm going to find the ratio of this guy when the non-hypothesis is true to when it is not true. When it is not true is this guy. I'm going to do the ratio of the two. Okay? And that is what I'm actually going to start from next time here. That's what you're going to see here. Can you see that? We find the ratio. And you know the beauty of this? When you find the ratio, you're only going to have the ratio of the two covariances. The covariance when the non-hypothesis is not true, divided by the covariance when the non-hypothesis is true. And that is why in multivariate analysis, okay, we care about relationship. And to care about relationship, you need to analyze covariance structure. I'm actually going to start from here next because we're using this material, this old material for the whole week. Okay. Before I go, I will advise you to start getting yourself familiar with meet and one practice question that I uploaded. But I'm gonna go over there with you on Monday. And don't forget your test is next week. Okay. But I'm gonna go over that with you on Monday. I'm gonna tell you, give you a lot of information about the exam, what you can bring to the exam, among other information. That's all I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone. For now, everyone.